Yeah, hello everyone. It is my pleasure to announce our speaker today, Franziska Meier. Franziska is a research scientist at the Facebook AI Center in Menlo Park in California. Before joining Facebook, Franziska did her diploma in computer science at the Technical University of Munich in Germany. She then did a master's and a PhD at the University of Southern California in Los Angeles, where she was supervised by Stefan Schaal. Afterwards, she did a postdoc at the University of Washington in Seattle, and she worked as a research scientist at the Max Planck Institute in Tübingen. And Franziska is one of the experts on robot learning. She did a lot of work on motion primitives, especially probabilistic formulations of motion primitives. And she also recently published papers on applying learning to improve locomotion and on robot manipulation. And for her work, she was also presented with the Best Paper Award at ICPR 2021, and she was finalist for Best Paper Award at ICRA 2018. And one big topic which runs through her work is the concept of lifelong or continual learning, the idea that robots have to learn in an incremental and continuous fashion. And this will also be the topic of her talk today, which is lifelong learning for robotics. Yeah, I'm really happy that she accepted our invitation, and here she is, Franziska Meier.
Thank you for this really nice introduction. Let me now reshare my screen. Okay. Okay. Yes. So as Andreas just mentioned, today I want to focus on the journey of lifelong learning for robotics for me. And I will focus more on the meta-learning aspects of it, which is what I'm thinking a lot about these days. So unfortunately, not so much about motion primitives, but I'm always happy to talk about it later if no one has questions about this work as well. Okay. So when I just want to kind of set the stage of where I'm coming from. When I think about robots, I kind of have this very ambitious view of I want robots to be able to do all of these things. I want them to be able to cook, clean, maybe even repair things, and many more things. Really, the spectrum of what I want robots to do is really just always growing for me. But I don't necessarily think that we should be trying to prepare robots for all of these things a priori. So we humans, we have the ability to learn many, many skills with really infinitely many variations. And these variations, for example, include different environments. And we are able to learn or adapt existing skills in these new environments, or like even just totally new skills that we haven't learned before. And that's kind of how I think about robots. So let's not try to prepare them for all of them, but enable them to learn them on the fly. That's sort of where I'm coming from. But in the robot learning community, we have this predominant assumption that I see always, that robots have this one-time training phase, right? We have a training phase, we train the robot to do something, and then we let it go in the world, and we hope it will be fine, basically. And there's like two main threads of related work that kind of exemplify this thinking for me, and this is the sim-to-real efforts. Like there are many, for example, realistic visual simulations being developed these days in the hopes that we can learn robotic behaviors in simulation, then transfer them to the real world. Or these more large-scale data efforts where we have arm farms or robot farms that can collect massive amounts of data for the task that they're supposed to be training for, and then and then again we're done training and the robot can just execute the behavior in the real world. And those are fine efforts. I don't have an issue with them, except I just don't believe that this will get us the robot that we want. I do think that we still need to also enable the robot to learn in the real world online, as it's encountering a new situation or a new skill to be learned. And so I have always this lifelong learning assumptions that robots will always have to be ready to learn and adapt. I should have added in the real world. So what do I mean by this? So I'll start making things a little bit more concrete now. So we have this robot, let's say it's seeing me or someone water the plants, and I tell the robot, like, I really would like you to be able to water the plants. The robot comes with a learning framework in my mind. It has some policy or models or like everything that it could learn. It has some way to initialize the model. It has learning rates. It has an optimizer, and also loss and reward functions, depending on whether you're learning models or policies, or whether you do self-supervised learning or reinforcement learning. I have this big umbrella, basically. This learning framework captures everything. And so now this learning framework should now somehow enable the robot to learn the skill autonomously. So this is the first part of my thinking, what we need to do to enable a robot to learn in the real world a new skill. We need it to actually learn autonomously. And by that, I mean, we need to minimize expert intervention. And for me, everything that goes into this learning framework is actually expert intervention, right? How to initialize the model, how to choose the learning rate, setting a loss or reward function. All of these things are expert knowledge. And without having this information, the robot actually right now can't learn in the real world autonomously. Then we have this axis of continual learning, where let's say the robot has already learned some skills a priori, so it has already learned something, but now we're encountering this new skill. How can we learn this new skill now without forgetting the old ones, right? This is kind of a very technical problem of how we represent skills often. If you have a big neural network, then just updating the parameters of the neural network will mean, there she goes. 1 second. How bad is it for you guys? Can you hear me, or?
Yes, we can still hear you.
Okay. Zelda, hey, come here. Okay, 1 second, sorry, she will not stop. Come here. I know, come here. You're staying with me now. Okay, so here she is.
Hello, hello.
Okay. I'll have her now on my lap so that she,
The name is Zelda?
Zelda, yeah. Okay, so where was I? Continual learning. Okay, when you update the parameters of a neural network, just based on the new data that you're seeing or getting, you will shift the parameters such that they won't be able to necessarily do, represent the knowledge that it has captured before. And so that's what's called, what is forgetting. And well, we want to prevent that. So that's the continual learning challenge for me. And then I'm always very driven with this learning in the real world. I actually want the robot to be able to do things in the real world. To me, this means I wanted to learn from a really realistic number of trials, but really what I mean is in a realistic amount of time, right? So as many trials as it can do in a fixed number of time. And I often think about this in terms of sample efficiency, because the number of trials are limited that you can do in a fixed amount of time. So yes, so those are kind of the 3 axes I think about. There are other things to think about when you think about lifelong learning, but these has been my main foci points. And today I'm gonna mostly talk about the autonomous learning part, which means how can we figure out how to learn these components of the learning framework. And this learning in the real world component, how can we learn from a realistic number of trials or observations? Okay, So just to kind of also ground how I think about addressing these issues when I think about autonomous learning, I think about meta learning or inverse reinforcement learning. To me, it is kind of some continuous slider, and you'll see why soon. And then learning in the real world. Right now, I tend to address these by trying out model-based approaches, so learning models, and utilizing structure when I have it available for these models. Yeah. Okay, so in the rest of the talk, I really mostly will focus on learning loss or reward functions. I will not touch the other ones, although I have some work on that as well. But just to give a coherent story, I will focus on learning the loss or reward functions. Okay, any questions so far, or are we all on the same page?
Same page.
Same page.
Good. Yeah, I haven't gone into anything technical yet, so should be easy. Okay, and okay, so let me start with talking about the paper that Andreas and I kindly mentioned that we won the Best Paper Award for. We presented recently work on how we can frame loss and reward learning as a bilevel optimization framework. As many of you might be aware, bilevel optimization has become very popular these days, and with that we get many libraries that are also gradient based, so we can just use these typical toolboxes, learning toolboxes, to implement bilevel optimization problems. And without going into too much details, we just have two levels in this bilevel optimization framework, where the upper level is optimizing the reward or loss function. And then there is an inner problem that uses this reward or loss function to either optimize the policy in the case of the reward, or the model if we learn a supervised problem. So we have a loss function basically. And in this work, we presented how this can be applied to learn for basic regression and classification tasks, so for supervised learning problems, but also how we can learn reward functions with model-based reinforcement learning or model-free reinforcement learning. And that all is very meta-learning oriented, but then we also have this extra piece of we can, during meta train time, add extra information or privileged information that help us shape the loss or reward function that we're learning. And for example, in the RL setting, what is useful is to add actually demonstrations at this meta train time. And so this is why I have this kind of continuous slider between meta learning and inverse reinforcement learning, because inverse reinforcement learning is has been concerned with learning reward functions from demonstrations. Yes, and we have code available for all of this at this link. So now in this initial paper of learning reward function, we had already touched on we can use demonstrations to shape the reward function with this bilevel optimization approach. But these demonstrations were these typical demonstrations of you have the full like state and action trajectory. So you have the coupled state and action trajectories. When I think about applying this in the real world, I really want my robot to just watch me without me having to guide the arm to show it how to water my plant. I just wanted to watch me and see what I'm doing and then try to repeat it with its own embodiment. And that means I don't think we should have access to actions, basically. And so we had a follow-up work where we took our learnings from the meta-learning paper and we tried to make it realistic for on-robot reward function learning from visual demonstrations. And that's what I'm going to dig into a little bit now. So this is the motivational slide of this work. We know as humans, even as babies already, we watch other people, even in TV, and then we just start repeating what we see. And the way we thought about it for the robot is we have someone demonstrating, that is, by the way, me in my home with the cooker arm. So we have me demonstrating the task of placing the bottle on a shelf. I want the robot to learn a reward function from that demonstration. And then I want the robot to use this reward function to minimize a policy or to optimize a policy such that it can execute the same behavior. That's kind of what we're aiming to do here. As I mentioned before, I take a model-based approach. So this policy optimization step really will happen with a learned model, where the model has been learned by the robot just collecting data of how its actions will change the representation. I will go into the representation of the object. Yes, so we have actions. The state is a learned representation of the object, and the next state is the next learned representation, basically, of the object. So we learn this model a priori, and then that's what we use to learn the reward function. Any questions so far? Zelda has some questions. And the reason why I'm taking this approach is because I really hope this will allow us with sample efficient learning of the policy. I haven't really evaluated yet whether a model-free approach would have worked as well, but yeah. So let me go into the details of how we optimize the policy first, and then I'll go back to how we learn the reward function. I will go over this a little bit fast, but please feel free to stop me. So we have a key point detector. This is what we use to represent the object. So we learned this key point detector initially, also on this data that I showed you, that where the robot is randomly moving around the object. We learn a key point dynamics model. I will talk a little bit more about this later. This key point dynamics model takes the actions of the robot, the current join state, and the current key points, and then and then predicts the next join state and the key points. The actions then, so this is then chained over a time horizon t. So we make these predictions for t time steps, and then we have a final predicted join state, and we compare this to some goal key point representation that we want. The cost is only formulated in the key point space, so we don't take the join state into the cost function. And then we minimize these actions by just performing gradient descent on these actions. So that's kind of the pipeline that we're using. So it's really more of a visual MPC approach instead of a policy learning approach, because these actions you are the parameters themselves, not policy parameters, but it's an easy step to move to a policy here.
Can I actually ask a question?
Yeah.
So you call it MPC in the sense of a receding horizon MPC, or you mean just in terms actually trajectory optimization?
Yeah, I use it in a very lax way. We have a model, we use the model to predict forward and optimize actions based on that, right? So it's more this model predictive.
Okay.
Yeah.
But what you get out is this sequence of this open loop sequence of control signals actually.
Yes. Yeah. And okay. We in this paper, we ended up then going open loop, which I find even more impressive, but we've also tried the receding horizon. It just didn't see, it wasn't necessary for those simpler tasks, I guess.
Mm-hmm. And the key point, so when the human demonstrates, does the human also have key points?
Yeah, so the key point detector is trained on the robot, but then it's also used to extract the trajectory of the object on the human demonstration. Yeah.
Mm-hmm. Okay, thanks.
Yeah, so training data, as I said, is the robot kind of going to random configurations in its joint space, and then only moving the end effector, basically, such that mostly the object moves. This is kind of an artifact of how the key point detector is being trained, because it tries to focus on variations in image sequences. And so we wanted to only have the object move. It still doesn't necessarily only capture key points on the object, but that's at least some of them would fall on the object. Then the key point dynamics is, I said we predict the joint state, but really we just integrate forward the action. The actions are delta joint configurations here. And the key point predictions is then a simple neural network. So that's done with a simple neural network. And okay, those were the details of those two components that were maybe still a bit fuzzy. And if that's all clear, then I will go quickly to the learning of the reward function now. Okay, so the reward function, I will try to explain the bilevel optimization a little bit more in detail right now. And I think it's easier to start at the lower level. So let's say we have a reward function given, then what we want to do is maximize this policy that gives us predicts us actions A given on the current latent state. We also have a model that predicts forward what this action will do, right? So actually this reward function takes the predicted latent representations. We maximize basically the policy, well, we optimize the actions such that the reward is maximized under our assumed model F, right? And this is the learned model F. So that's what the inner loop does. And it passes this predicted trajectory out. And this predicted trajectory in your mind now is a function of the reward function, right? And this is what the bilevel optimization frameworks do for us these days. It actually keeps track of these gradients. And this the reward function parameters is what we're optimizing in this outer loop now, based on, we have this predicted trajectory, which is a function of the reward. And we wanted to match the demonstrated trajectory. And so now we're minimizing this distance by adapting the reward function parameters. So that was a mouthful. I hope it's intuitively a bit clear. That's the level of detail I will stay at today. Yes, so that's what we do. This trajectory is completely in latent state again. So we really can just take a visual trajectory and try to use the robots model that it has built of its own embodiment to find a policy that matches this visual trajectory as best possible. And so now some results. This is me demonstrating this. You see these key points. They're not very robust necessarily. And we have tried out various reward function. And I just want to point out the one on the right-hand side is the one where we use a default cost function, which is just the mean squared error between the goal key points and the so basically, and the demonstrated trajectory and what it's doing basically. So it's trying to it's just trying to optimize to the goal key points. Exactly, that was our baseline. And you see it starts colliding with the shelf. So it just didn't capture that the demonstration basically, because it doesn't have the demonstration, right? So it doesn't capture that it should first move over the shelf and down. And then these three here, we learn various cost functions that that were trained by trying to match the demonstration. Basically, the cost function itself doesn't take the demonstration into account, though. It only takes the goal key points into account. And then you see the different results. The time-dependent ones outperform non-time-dependent cost functions. Yeah, so that was that part of learning from visual demonstrations. let me skip quickly because, yeah. We have this assumption here that we can learn in this whole framework. One of the biggest issue was this assumption that we can learn this model. And ideally in my world, I really want the robot to learn this in a self-supervised manner. But this is actually incredibly hard to learn. So we tried to just have the robot similar for the key points that the data that we collected to learn the key points. I just wanted the robot to do some not random, I mean, I did some sign motion behaviors on the robot to get data that covers sort of the state space and then learn this model from. So it was very naive in a way. I thought that should just work, but it didn't. What we ended up having to do was actually implement an expert controller to do the placing tasks such that I can get data around this trajectory. And then we were able to like collect data for around this trajectory and learn this model. And then I threw away the expert controller again and said, okay, now we pretend we don't know how to solve the task and see if we can learn it from visual demonstration. And that was, of course, frustrating because the goal was to be totally autonomous, but then we weren't because we needed an expert controller to actually collect the data. So I kind of started to think about how can we use structure here to make this learning of this model easier. And the reason why I go for structure is because there are several challenges of why this learning of this visual dynamics or predictive model is challenging. So first of all, the very basic thing is we're predicting to the image key points. And this predictive model is then learned in 2D space, but control happens in 3D workspace. Then the key points, they don't necessarily fall on the object and are not forced to consistently track the same part of the object. So that makes it hard to learn a predictive model as well. But then most importantly, these neural networks, they just are very poor at generalization to parts of the state space that they haven't seen. And in this case, it was not just extrapolation, it was also interpolation that didn't seem possible. Maybe we didn't collect enough data, I'm not sure, but that's the failure point that I identified. And that now comes to the second part of what I wanted to talk about. So someone will have to stop me when I'm running over time because I have, I think, too many slides. And so here is where I come to the question of, okay, learning, like we could have gone with either collecting more data, but my sense was this would require a lot of data, if it's even possible to get enough data with the other challenges that we have. Or can we utilize structure to make this better? And we went with the utilizing structure. And this is the structure that we infuse is a differentiable robot model that we implemented, where we have in PyTorch, we have a representation of, let's say, the KUKA arm. Each link is its own PyTorch module, and we can add new links, like a link for an object, basically, at the end. And each of these link modules is parameterized by either kinematic parameters or dynamics parameters that we can either take from the URDF or we can try to identify from data. So this is that's what I call a learnable and differentiable robot model. And I'm now going to try to infuse this into this model that we're trying to learn, this visual predictive model. This visual predictive model is really a kinematics model in a way, right? Because if you knew how you picked up the object and you knew the object dimensions, you could, through kinematics, compute like the endpoints, like some of the key points, maybe locations that you wanted to know about. So what we will do is actually learn this, use the differentiable kinematics in this project now to improve this model's performance. Okay, let me skip this right now. The first step we actually did is we tried to figure out if we can use this differentiable model to improve the key point prediction, because we're really unhappy with the key point predictions. Some of them were just not on the object often, so we had to go through a lot of seeds to find one key point detector that would give us kind of 3 key points on the object. What we ended up doing is, so what you just saw was the pipeline that how the key point detector is trained. Usually you have a image, basically RGB image, a ResNet that encodes some visual feature map, and then you have a key point. These feature maps are basically mapped through a bottleneck, which are the key point probabilities, and then from the key points, it tries to reconstruct the image. And this is really trained on an image sequence. So when I say it's trying to reconstruct the image, it's actually trying to reconstruct the changes in the image sequence. And now what we did say is, oh, let's just use our kinematics model and add it to the this key point learning framework. Let's say we also have calibration of the camera. Then we can project the end effector into this image, and we can kind of try to bias the feature learning towards the end effector. And that's what Sarah did. I forgot the paper title here, but please feel free to ask later. This sort of simple approach. So we have this kinematic feature map and then the visual feature map, and we just add them up, and that's all we did. This is it's actually very powerful. What we saw was that we found some criteria to measure how close the key points are to the actual object, and with this bias towards the end effector, our approach consistently produced key points that are actually on the object instead of somewhere in the world. So that was nice. And then an interesting different experiment we also did, which is related to sample efficiency for me, is that Sarah tested whether we actually need this proprioceptive information. So we do need joint state information to get the end effector location in image. Whether we need this for all the data points or whether we can just have partial data. And this is kind of the experiment where she has a complete data set of, let's 100%. And then she takes none of them have proprioceptive joint state information, 25%, 50%, and so on. And then again, the metric of the distance from the center of the object, so how the key points, how close the key points are to the object, basically. So lower is better in this case. And what we see is that we don't actually, around 50%, we already get pretty good results. So we only need really proprioceptive information for half of the data. So which in my world translates to, we only need 50% of interactive data, like of the robot actually collecting data in the real world. And then otherwise it could use passive data, like me manipulating the object, right? So it could take data watching me move the object around. So that I found interesting. I wanted to kind of highlight that. Yes, and so just to give a visual depiction of what this looks like is, this would have been a typical, on the right hand side, this would have been a typical result of the key point detector if we didn't filter specifically for one that looks good. And this is a very consistent result that we get, that the key points actually fall on the object. But then Sarah didn't stop there. What she then also did is say, okay, so now we don't want to use this neural network to predict the changes in key point. Basically, if the robot applies an action, we want to learn actually an extended kinematic chain. That's what we call it. And so we go back to our differentiable robot model, where we add now an extra, actually we add 3 links, one for each key point. So we assume we know how many key points we're learning. And we just try to identify the position of each of these key points from the visual key points. And Sarah formulated this as a regression problem, and she was able to learn these key points from very few, I believe she said like 15 data points, and is able to learn the key points and attach them to the differentiable kinematic chain. And the red points here now mean they are attached to the kinematic chain instead of just visually detected. And then we repeated this experiment with this kinematic chain, and it was just way simpler and easier to make it work like this. I hope this was clear. I know it's a lot of information, but I'm going to throw one more table at you now, and that is basically that we did this comparison of comparing this differentiable kinematic chain where we identified the object key points, links, parameters from data versus we learned a predictive model with a neural network. And Sarah did this experiment where she tried to predict forward on a time horizon of 25 time steps and to see how much it diverges from the ground truth, basically key point state. And the labels are very bad here, but basically orange is the differentiable kinematic model, and the others are variations of this neural network with also where we also try to include 3D information so that we actually have we actually use the depth for this experiment as well. I believe this one, the one that is baseline D, is the one that uses 3D information. But in the end, it was not enough to get long horizon time prediction, basically. So at some point, all of these neural network forward predictions, if you unroll them over a time horizon over, multiple time steps, they diverge very fast from what is actually happening. And this translates into the actual downstream task when you're then trying to control the placing task, right? So when you use the model to optimize actions to perform a task, then you see a very fast like divergence, basically, the longer the task is. Yeah, that's all I have today. I have many collaborators that helped with this work, and I talked specifically about 2 projects that we also open sourced so that you can find the code here. And that's it.
Thank you.